Hello everyone, thank you for tuning in. My name is Yongshan Ding. In this talk, I will introduce our recent work at Micro 53rd on how to mitigate crosstalk errors for superconducting qubits by frequency-aware compilation. It is our most recent example of quantum computer system design in the presence of hardware noise. This is a joint work with my colleagues at UChicago and is funded by the EPIC collaboration and NSF Expedition in Computing. To mitigate crosstalk, we need to first understand what it is. We can define crosstalk as roughly as an unwanted interaction between qubits. We focus our study on superconducting transmon qubits, one of the leading implementation of qubits. Here, interaction means some form of energy exchange. In this figure, 4 vertices denote 4 transmon qubits, and 2 qubits are connected if they are coupled physically and allowed to interact. During idle time, nothing should happen to the 4 qubits, but if Q1 and Q2 are on resonance by accident, meaning the 2 qubits have equal or similar frequency, they would cause crosstalk, resulting in a correlated transformation epsilon acting on the 2 qubits. During operation time, we execute 2 quantum gates U1 and U2 by bringing Q1 and Q2 on resonance and Q4 and Q3 and Q4 on resonance separately. If, however, all 4 qubits are tuned on resonance, then U1 and U2 become some epsilon transformation acting on all 4 qubits jointly. Such crosstalk error prevails in today's quantum devices and hence preventing us from scaling up to larger systems. A number of hardware strategies have been proposed to mitigate crosstalk. First strategy is to build a device with sparse connectivity so that fewer pairs of qubits are allowed to interact with each other directly. While it successfully reduces some crosstalk, it also hinders the ability to execute gates, as 2-qubit gates now induce high communication costs. Second strategy is to implement tunable qubits, so that we can dynamically adjust the frequency of each qubit independently to avoid unwanted resonance. Shown here on the bottom right is how we can use external magnetic flux as an external control to change qubit frequencies. Third strategy takes one step further by allowing couplers between qubits to be dynamically switched on or off as well. Shown here, the gray boxes between the 2 qubits are switches for the coupler. Different hardware designs have different costs. In general, more tunability is harder to build. In this work, we propose a compiler framework via hardware and software co-design. We demonstrate how to actively tune system parameters such as qubit frequencies according to input programs, trading parallelism for higher gate fidelity when necessary. Our methodology has a notable feature. It reduces a complex physical problem to a number of scalable computer science subproblems, such as graph coloring and set solver. Here's an overview of our strategy for crosstalk mitigation via frequency-aware compilation. Starting with any quantum program, the first step is to translate to a quantum circuit mapped to a quantum device. As mentioned, parallel 2-qubit gates may cause crosstalk, highlighted in red here. To prevent accidental resonance, we propose 2 general solutions in the compiler, namely temporal separation and spectral separation. Specifically, if we decompose parallel gates into native machine instructions of different types, the two qubit gates are hence separated in time, as shown on the right-hand side with the green box. Alternatively, we can still allow them to be performed at the same time, but assign different interaction frequencies for the two qubit gates, shown on the left with spectral separation. In particular, here are some examples of gate decomposition we used to implement temporal separation. Spectral separation is accomplished via a combination of optimizations, including graph coloring and set solvers. Consider assigning two sets of frequencies. When idle, qubits are parked at their idle frequencies. If we use different colors to represent different frequencies, this checkerboard pattern on the left of two colors is sufficient to isolate any vertex from its nearest neighbors. When performing a two qubit gates, denoted as a red edge in the middle of the center figure, all nearby qubits must be tuned away from its interaction frequencies. Shown on the right-hand side is an example assignment of interaction frequencies for all edges for all pairs of qubits without any collisions. So in general, coloring a device connectivity graph shown on the top row gives a solution for idle frequencies. Interaction frequencies can be determined by coloring the crosstalk graph shown on the bottom row, where vertices are possible two qubit gate locations and two vertices are connected if the pair of two qubit gates could result in crosstalk. Notice here that we only color an active subgraph of a crosstalk graph, highlighted in red, for example, on the bottom left figure. Only a subset of qubits are involved in the two qubit gates at each time step. So we only need to color the subgraph of the crosstalk graph for that time step. Once the graphs are colored, we can finally translate colors to frequencies by writing down a constraint satisfaction problem. Each qubit has a range of tunable frequency and some constraints such as resonance and leakage with its neighbors. Putting it all together, we obtain idle frequencies for qubits by coloring the connectivity graph using the Welch-Powell algorithm. We obtain interaction frequencies at each time step of a program by identifying and coloring its active subgraph of the crosstalk graph. We map colors to frequencies using SMT solvers such as Z3, accounting for realistic hardware constraints such as leakage. So showing on the very end of the right-hand side, you can see the resulting frequency values that we assigned to each qubit for their idle frequencies and for each pair of qubits for interaction frequencies. In terms of performance, this figure shows that our software method, denoted as red bars, achieves more than an order of magnitude better program success rate than the serialization approach, denoted as yellow bars, or baseline U. And comparing with baseline G, which is based on the Google Sycamore architecture, we found that our method achieves comparable crosstalk mitigation performance, but with simpler hardware, that is, no tunable couplers. This is a great example of how a software solution, co-designed with hardware, accomplishes drastic systematic performance gain. To provide insights into the general applicability of our algorithm with respect to device connectivity, We tested the performance of a wide range of connectivity graph, both sparser and denser than 2D grid. Denser graphs offer better connectivity, but they're harder to build and a lot more crosstalk channels that could happen. We target a class of connectivity graphs with increasing density while incurring minimal wiring overhead, namely the express cubes design, which is originally designed for interconnection networks. For example, 1x2 represent a graph constructed from a 1D line by inserting an additional connection every 2 nodes. Results are promising. These figures show that our algorithm outperforms the serialization approach by about 4x on average, with desirable compilation time overall. It scales favorably with system size, making it a viable long-term solution to frequency tuning for superconducting qubits. And with that, thank you for your attention, and welcome to attend our session at Micro, session 2A on Monday, and feel free to ask a lot of questions, and hope to see you there. Thank you.